Hey everyone, welcome to a new video. It's Federico here, and today we're going to see how we can recreate this effect called Pixel Rain in Max using OpenGL objects and some good old shader coding. The idea for this video came to me when I was watching this tutorial from the channel Frank's Laboratory. The tutorial is called Vanilla JavaScript Pixel Rain tutorial, and is about creating exactly this effect. Now, this effect is created by the author in JavaScript, so vanilla JavaScript, and we are going to see how we can convert it to Max, basically taking the algorithm and porting it to the Max world. Now, this channel is amazing, as a lot of other tutorials, so I encourage you to check it out. I will put a link in the description. So the idea for this algorithm is very, very simple. So first of all, we have X particles. Then we have an image, and then the particles fall down. So the speed at which the particles fall down is based on the brightness of the pixels on which the particles are currently passing over. So if a pixel is brighter, the particles will go slower, and if a pixel is darker, the particles will go faster. So if you take a look at the reference image, it's this Fox image here. So you can see that the darker areas, the particles are accelerating, and on the bright areas, the particles are going slower. And this creates this effect of this pixel rain. But it looks almost like the particles are pulling up like in a waterfall and then keep on falling down. So this is a pretty cool effect, especially like when you start it for the first time on an image, which creates this very cool effect. So yeah, it's that simple. And we know on which pixel the particles are because we use their position to sample the pixels of the image. So let's see how we can do all of that. Okay, so we have our patch, and the first thing we need, as always, is a JIT world. So let's give it a name. Let's call it Pixel Rain. Let's give it floating 1. Let's give it initial size. Let's give it a raise color black. And let's give it full scale anti-aliasing as well. And let's also enable it by default with enable 1. Okay, this should be it. Let's create a toggle to toggle it on and off. Let's create a jit.fps GUI to check our frame rate. And actually, I want to have a frame rate of 100 frames per second if possible. So I will set the FPS to 120. Also, I have to set the display link to 0, so the frame rate will not be linked with the refresh rate of the screen. And the reason why I want to have it at 120 frames per second will be clear later during the tutorial. So cool, the first thing we need is something to create our particles. And indeed, we're going to use a GL mesh, which draws to pixel rain. And we want to set its draw mode to points. And maybe let's give it a color of white, and let's also increase the point size to something like 7. And for the moment, this is going to be it. So if we now create a JIT noise with 3 planes, float 32, and let's say we want to have 10,000 particles, can attach it to the first inlet of the GGL mesh, bang here, and you will see that the points appear as particles. Now, we are actually in a 3D world, but for this effect, we actually don't need the third dimensions, right? Because it's a 2D effect. So what we can do is to go into our JIT world and set orthographic projection to 2, which means it will actually be an orthographic projection. If you will set it to 0, will be perspective projection as it is by default. Ortho 1 is also orthographic, but uses the lens angle, which we don't care about. So Ortho 2 is exactly what we need because we want to work in 2D. We don't want to care about the third Z dimension. So what we want to do is to use the GPU for this algorithm, for this effect. So we want to apply movement to the particles and want to modify some other attributes of GGL mesh through the GPU. So what we're going to do is to use the JIT GL TF object, the transfer feedback object. So let's see in a little scheme how the GGL transfer feedback works. I think I showed it already on a tutorial of mine, but it doesn't matter. I will just show it really quickly. So let's give it just 3 inputs with the number 3, and let's open a little paintbrush. So let's imagine this is our transfer feedback, and what happens is that the transfer feedback relies on a shader. So this is our shader code, which does something for the vertex shader of the GGL mesh. So basically modifies the vertex properties of the GGL mesh. Then the output of this shader is fed back inside itself, inside the shader. So if we set the position of the particles to something in the shader, when we input it again, the input position will be the position that we output in the previous frame. Okay, so in this way we can keep updating the position of the particle. So if we start with our particle here and then we update it and now our particle is here, in the next frame it will not start back from the first position, but will start from our updated position, right? So then we can update it to go somewhere else. That's how the transform feedback works in a very much nutshell. So let's go back here on the practice and let's create a shader, because we will need a GGL shader object to interact with GGL transform feedback. This is going to draw to pixel rain. Let's give it a name and let's call it rain shader. And let's actually give it also the file attribute. We will call it rain shader.jxs. This file doesn't exist yet, so let's double click on the shader. You will see it will open the standard shader that Max creates for us. So let's go here, let's save us, and I will put it inside this folder where I'm saving all the patches and files relative to this tutorial. And this is called pixelrain.jxs. Cool, now I close it. Now, if I double click on it, you will see that it will be open inside Visual Studio Code, because I set these from the Max options. So if you go into Max options, Max preferences, you can choose the external editor. So always use external editor, and then you can choose it with this choose button, which external editor you want to use. I'm going to use Visual Studio Code as I always do. And I have also this highlighting for GLSL syntax. So it will highlight all the stuff that are relative to GLSL. Cool. And as you can see, this shader is not really made for GGL transform feedback. In fact, it has also geometry shader, which we don't need at all. So we can delete all this part between program name GP and the closing tag program. Right? So we are left with our vertex shader and the fragment shader. In the fragment shader, actually, we can delete everything apart from the main function, right? But we can completely empty it. I'm not sure this is actually necessary to keep, but I've always seen it like that, so I will just keep on doing it like this. Now, the model view projection matrix, we don't need that. We don't need also this out structure there. So we also don't need this line here in the param declaration or in the param binding, right? There is a description here. We will just write pixel rain shader for TF. Cool. This is just, it's not code. It's just something that it will be useful for the people that read the shader code. Doesn't make anything to the actual code. So here we don't want to set the GL position. We don't want to set the GL color. Cool. And that's basically our starting point. So what we actually want here is to create a bunch of GGL buffer objects. Now the buffer object is simply an object that mirrors a vertex attribute of the GGL mesh. So if we connect this to a GGL transform feedback, this buffer will be filled with the result of the output of the transform feedback and will change consequently the vertex attribute of the GGL mesh. So let's connect the GGL mesh to the GGL TF. And the GGL buffer takes as attributes the type of buffer. So this is going to be the position buffer, which means the position property of the vertices of the GGL mesh. And then we need an out name. And we're just going to call it O position. So out name is basically, if you remember this drawing, this awful drawing I made here, in our shader, we have like an input, so I position, let's call it. And then we have an output position. In this case, we call it O position. And this means that what we write to the O position variable, it's going to be equal to what will be inside I position in the next frame. So we need to specify this name manually because otherwise Max will be very confused. So we say out name O position. And then I'm not even sure we need 3 inputs. We probably just need 2. So let's create another one. This is going to be of type color. And the out name is going to be, you guessed it, O color. So this will modify the color property of the vertices of the GGL mesh. So let's connect this here. Now the transfer feedback, we need to give it the name of our shader. So it has a shader attribute and we set it to pixel rain. This is the shader that we're going to use to control the transfer feedback. Oh, and by the way, if you never heard about all this transfer feedback stuff I'm telling you, if you go into extras and then you go into GLCORE examples, you can see what this is about. There are also a lot of docs about working with GLCORE, which was previously called GL3. And basically this is all about this transfer feedback stuff and some more goodies that are only available with the GLCORE. With that out of the way, let's connect this JIT noise to our buffer position. Let's actually create then a JIT matrix with 4 planes, float 32, same number of particles, of cells, which will be our number of particles. And let's set these all to 1. And then bang these inside this GGL buffer. This is just to set to something, because these buffers must be filled with something. I guess we could just send a load bang here. We don't really need to set any value inside this matrix, but we definitely need to bang it. Otherwise, the transfer feedback will complain that it doesn't have any input data. Cool. And once we did that, let's go inside our shader. Let me actually move a bit the patch here to the left so we can have our shader here on the right. And as we said, we want to have output variable called oPosition. And this variable is a vector 3 because it's controlling the position property of the vertices of the GGL mesh. And then we have another one, which in this case is going to be a vector 4. What did I write? Vector 4, and this is called oColor. Right, now our input variable. So as you can see, we have these input variables. Let's them actually call iPosition and iColor. So we know that these are the inputs. So we have to change the name also here on the param name declaration. Oh, and if you don't know anything about shaders in Max, I have a lot of videos about this. I will put a link in the description, so you can use those videos as a reference to understand what's going on here. So iPosition and iColor here. Cool, once we did that, we actually need to assign the output position some value. And for the moment, we'll just set them to the same value as the input position. So oColor is going to be equal to iColor. And oPosition is going to be equal to iPosition. If we will not do that, the shader will definitely complain. Now, it's already complaining because it seems that I broke the XML formatting in some way. And you know what I did? I forgot to put this quotation mark here. Somehow I forgot a quotation mark. Right. So now it should be all happy, not complain about anything. So inside the GGLTF, there is an attribute called enable. So if we enable that, it will, it requires a valid shader. And this is not a valid shader because I actually misspelled the name. So it's not pixel. Pixel rain is actually the name of our world context. This is actually called rain shader, our shader, right? So let's see if this now works. If it works, it should not happen anything, and indeed nothing is happening, but it's still rendering our particles, which is great. It's not complaining, so it seems that everything is working. Now, to be super sure that this is working, let's just add a small value to the epsilon position, like 0.001. And if this is working, yeah, we should see our particles going down, which is exactly what is happening because we are subtracting a small quantity for each frame from the epsilon position. Okay, so it's working, great. As you can see, where the epsilon position of the particles is below the number -1, they just disappear out of the window, right? To never be seen again. So we will need to fix that later, so we can actually just fix it now. We can do something like that. oPosition, so let's actually create a new variable here. Let's call it new position, vector 3. It's equal to iPosition plus, actually it's equal to that line here. So we can say if new position dot y is less than -1, so it means the particles are outside of the window. So let's actually write it here. Particles went to the bottom of the window and disappeared. So if they went to the bottom, let's actually put it here. If they disappear on the bottom of the window, we can say that new position.y is equal to 1. So it becomes then the top of the window. And let's set this equal to new position. So if we click here again, let's make the go a bit faster. So by making this number 5. Okay, now you can see that when the particles go on the bottom of the window, then they will reappear here from the top. Awesome. This will be useful for us also later for our rain effect, right? Cool. So what we need now is we don't want the particles appear like in a square fashion. Inside our window, we want them actually to appear all at the top of the window and then slowly descend on the bottom and then reappear on the top. But we don't want them to appear on this square. So what we need to do, we can create here a JIT-gen, give it a title and call it init position or something. And if you noticed, when I'm on GLSL, I like to use this camel notation, which means one small letter followed by a capital letter. So if I should create a variable like my own little vector, you will see that I will use a small letter followed by a capital letter for the next word that make the name of the variable. And this is called camel notation. This is what I use in code. But in Max, I prefer to use this underscore notation, which is what Max prefers. For example, if you check the attributes of objects, let's see here, matrix mode async, for example, you will see that Max uses this underscore naming convention instead of the capital letter. So when I'm working with Max names that I have to choose, I usually use that. And when I'm in code, I usually use this camel naming convention just to make things super clear. Anyway, what we want to do inside this JIT-gen is to simply get rid of the second input first of all, and then we want to switch one single plane of the input, and we want them to appear to cover the whole window, right? Or at least between -1 and 1 on the x-axis. So let's scale the 0 and 1 of the noise to 1 and 1. And we can use that as the x position, otherwise the y position is going to be 1, so they're all going to appear at the top, right? And let's see, right, if they now are all lined up here at the top, if we click here, we can see that they will all fall down at the same speed. Cool. So the thing is, we don't want them all to fall down at the same speed, and we don't have really a way to create a random number that is going to be the same for all the frames in our simulation inside the shader. So what we want to do is actually, I guess, to create a new buffer and give these particles an initial velocity. So let's actually connect the color here. Let's just copy this buffer, and this is going to be type normal. So the vertex attribute that we're going to use in this case is the normal of the vertices, but we are not really using it as a normal. This is actually going to be our random velocity, right? This is what this is going to be. And then we can connect this to the GGLTF. And we are going to set this in initial random velocity from inside this JIT-gen. So let's create another output, and let's use another plane of these random numbers input. So for example, we can switch the second plane and say, okay, this is going to be the initial velocity, which is going to be this random number multiplied by something really, really small and also negative, because the particles have to go toward the bottom, right? So we need a negative number for the velocity, and then we can just attach this here. And this is going to be the initial velocity for the particles. Let's connect this to this buffer. Let's bang it. Okay, so inside here we need to add this new buffer to our code. So this is going to be I random velocity and state normal, right? Because we gave it type normal. And this is going to be a vector 3 as well, because normal is a vertex attribute that is made of 3 components, so it's a vector 3. Here we can then bind it, I random velocity. Inside here we need to create it as an input, I random velocity, and here as an output. So out, vec 3, or random velocity. same name that we gave it here to the buffer as the output name. Cool, and now instead of using this vector that we created ourselves, we can use our random velocity. Right, so let's see if this actually works. Doesn't work, but I haven't got any error, so it must be a logical error. Oh, and of course I'm using O random velocity instead of I random velocity. Plus, as I mentioned you, it will complain if we don't assign anything to the output variable. So let's actually do that. Let's simply assign the output equal to the input. So let's see now it works. Right. So each particle now is dropping down with its own speed, with its own velocity. Cool, that's exactly what we want. So we're actually at a good point inside our algorithm. There is not really much more to be done. What is to be done? It is that if you notice in my original patch, the particles are leaving a trail. So we need to set up this mechanism for particles to leave a trail on the window. And to do that, in the past, or at least when using GL2, so if you go into max preferences and you set GL2 from the graphics engine, you will just need to set the erase color alpha to a number smaller than 1 to have the particles leave a trail, but we don't like that. We actually like to work with GLCORE. So what we need to do in this case is a bit more convoluted. What we need to do is to create a GGL node that draws to our pixel, rain context. Let's give it a name, and let's call it a node, rain node or something, rain node. And then this node needs to capture our scene. And also we need to set the erase color attribute of the node to 0. Let's also set the full scale anti-aliasing of the node to 1. Cool. And we need our GGL mesh to actually draw to this node. So instead of drawing to pixel rain, it needs to draw to rain node, right? So if we create now a GGL video plane with transform reset 2, and this also actually draws to pixel rain, we can see that we still have our scene. It's just now being rendered to the node instead of to the main context. And what we want to do now is to create a GGL slab with a file called, I have this package from Timo, which I think creates aliases for all the shaders from GGL slab. It's super useful. If I remember, I will put a link in the description. Anyway, I just need to write GGL slab accum erase. Otherwise, you need to write explicitly that the file is called coaccumerace.chxs. So this is a GGL slab, another object to work with shaders. And if we double click in it, it will open the shader in Visual Studio again. This is the shader that comes with Max, and we can use the shader to create this trail effect. So how does it work? We need another texture, GGL texture, and this draws to rain node. So the output of this goes into the second input here, and this GGL slab goes inside the GGL video plane, so it creates kind of a feedback loop here. And as you can see, the particles are already starting to leave a trail. Now, if we want to control the amount of trail the particles leave, we can say prepend param, and there is an attribute in this shader called erase color. And let's actually set it to 0, 0, 0, 0. And if we go to check inside the shader, we can see that indeed there is this attribute called erase color, and this is the fade amount. So we can, actually we should not prepend that, but actually pack it, sorry. So this is to control the alpha with a Flona, and now we can see that if we make the alpha really low, we will have our particles leaving a super long trail. If we make the alpha a bit bigger, the trail will not be so long. So 0.03, I think it's a good amount. So I will just load mask that. Great. So now it's starting to look a bit more like this pixel rain effect. Awesome. Okay, so what we need now is the image, right? Because this whole thing works through with an image. So loading an image in Max is much easier than do it on the canvas in JavaScript on a browser. So for that, We just need a JIT matrix. We don't need to specify anything. Just need to say import movie and then maybe a bang. So when the matrix finished importing, we can bang directly the image out. So let me get an image. I like this fox though. I think it's pretty cute. So I will get the image of the fox. And then we need to pass this image to our transform feedback shader because this is where the action is happening. So we need to put this image into a texture. So let's create a texture. This draws to rain node and we need to give it a name. I will call it target image, right? And then we pass the matrix to this texture. Great. And then we can use this texture. Let's actually first display it. So let's actually create another video plane. No transform reset because we don't want to cover the whole screen with that. And we also want to say depth enabled 0. And then we want to draw it before our particles. So let's try if this worked. This didn't work. Okay, so this doesn't work because I think we should say depth enabled 0 here and then blend enable here. And also as layer, we should say 1 to that. Right. Now is working. So they are both drawing to the main context, these two video planes. This is drawing behind the other one. Now you can see that this image is being rendered as a square, but the actual image proportions are not square, right? Is more like, I don't know, full HD, but on vertical. Actually, we can find out what are the dimensions of this image with the dimension attribute of the texture. Okay, it's very big, actually very big image. So what we can do is to rescale this video plane to match the proportions of the image. So let's do it with a JIT matrix info object. And then we say root dimensions. This is going to give us the dimension of this matrix, of this image. And then we can just divide the dimensions x by the dimension y with a simple divisor here. This will be the proportion of our image. And then we can use this value to scale the video plane. So we need to scale the x of this video plane according to that value. And there we go. The image is now correct. That's the correct proportions. Let's try shortly to disable this other video plane. And cool, now it looks correct. Okay, cool. So now that we have our image in place and we have it inside the texture, we can pass this texture to our GGL transform feedback mechanism here. And we do that through setting the texture attribute for the GGLTF object. And we need to set it to the name of the image, which is called target image. And inside our shader code, we can now say, oh, this is the accumulates here. We can say param name, this is going to be target image. It's of type integer because textures in GLSL in max are of type integers, which means this is their index. It's not a state value that we pass into the shader because it's not created by max, it's created by us. So we just say default and the value that we want to have it, which is 0. And then we can bind it. So let's just copy this line. Let's say this is called target image. It's not an input variable. As you can see, it doesn't have this I in top. I didn't put an I on top. In fact, it's actually a uniform, which means it's a uniform for all the vertices of the mesh. So it's the same for all the meshes. Sorry, did I say meshes? I meant vertices. It's the same for all the vertices, while the position, the color, and the random velocity are different for each vertex. So this texture is of type sample 2D. It's called target image. There is something actually I forgot, which is to set the rectangle attribute of this texture. By default is set to 1, which means this texture can be sampled using, or must be sampled using integer coordinates, but we don't want to use integer coordinates, we want to use normalized coordinates, so we have to set rectangle to 0. Instead our shader, we want to set it through normalized coordinates, we want to sample it. So yeah, rectangle 0 it is. Now, inside here, let's get the value of this texture. So image value, or image val is going to be equal to texture. And this is the function to sample the the sampler 2D. And now we need some texture coordinates. Now the texture coordinates, as we said, are the position of the particles. So we need to use the position of the particles as coordinates for sampling the image. But our particles go between -1 and 1, right? So this is our 3D world. The y position go between -1 and 1. But our x position goes between minus window ratio and plus window ratio, right? So this could be like minus 1.3 and this 1.3, depending on the size of the window. So the texture coordinate go between 0 and 1. So if our texture here is in the middle is a square, the texture coordinate will go between 0 and 1. So we need to, and also on the y axis, 0 and 1. So we need to rescale our particles position into, from whatever it is. At the moment it goes between -1 and 1 on the x-axis and -1 and 1 on the y-axis to 0 and 1. So in order to do that, since for the moment it just goes between -1 and 1, since we set it here, 0, we scale the random numbers from 0 to 1 between -1 and 1. So let's create this variable back to text chord. Oh, and I forgot an x here. So this is equal to I position dot x y plus 1. So plus vector to actually 1. So now the particles the position of the particles is rescaled between 0 and 2. And then we just subtract 1 to that. So now it goes. What am I saying? Then we divide this by 0.5. So we divide by 0, multiply by 0.5, right? Cool. So now the particles coordinate, the particle position is rescaled between, so let's actually write it, rescale particles position from -1 to 1 to 0 to 1, right? Which then we can use as texture coordinates. Cool, and let's use this image val to modify the velocity of our particles. Let's say that the brightness we want them to be, then the slower they must go, right? So let's create a new variable here. It's a float. Let's call it speed. And let's say the speed is equal to 1.0 minus image value. So we reverse it. So speed is going to be greater if the image pixel, the image value here is bigger. But of course, image value is actually a vector 4, so I cannot just subtract to the number 1 and have a float as an output. So I actually need in some way to get it as a black and white image, right? Because I just want the brightness of the image. So to get the brightness of the image, let me create actually another function to get this brightness. Get image brightness. So it takes as an input a vector 4 image, or pixel actually. Takes a pixel as input. Okay, so the video tutorial that I showed you in the beginning gets the image brightness adjusted for human perception, which means it multiplies the red, green, and blue component by themselves and by these numbers, and then gets the square root of this value to get out the adjusted brightness. I don't remember exactly how this algorithm is called to get the image brightness. I think it just gets luminance adjusted for human perception. So it works like this. Let's create 3 variables. The red is going to be, for example, to pixel.air multiplied by itself. And now this whole thing is multiplied by this 0.299, right? And then for the blue and the green. So the blue is going to be pixel.p, oh, actually this is the green, right? So the second is the green, multiplied by 0.587. And the third one is the blue. This algorithm is not super necessary, just to have it a bit more, the brightness a bit more correct for the human perception, but it's not something that will break the algorithm if you just don't do that, but just, for example, sum red, green, and blue together and then divide by 3. So then let's return the square root of these 3 numbers summed. This is the algorithm. plus green plus blue. You can see this algorithm used in the original tutorial. It also explains it much better than what I did. Let's create here a new float value. Let's call it image pixel brightness or something. So actually image val, this will be better called pixel value. So pixel brightness, we can use then our function get image brightness using pixel val. And then we can say this number is between 0 and 1, right? So this number that comes out of here, if you make the calculations, is always a number between 0 and 1. So this is always a number between 0 and 1. So 1 minus that will give us the opposite of that, the negative actually of that. And then let's multiply the speed by something small. Let's create a new vector tree called new velocity. And this is going to be equal to vector 3 with 0 for the x, because we don't have any velocity on the x-axis. On the y, we get e random velocity dot y plus our speed, and then 0 for the zeta velocity. So when the image is the most bright, the particles will go slower because this number will be bigger, and so the particles will just move at random velocity. And when the brightness is lower, the particles will move at random velocity plus a number very close to 1 multiplied by 0.002. So new velocity is then going to be summed to new position. So if this is even remotely works, yes. Oh, you know what? They're actually being slowed down because this is a positive number which will push the particles up. So we actually need to multiply it by a negative number. And now it's better. I mean, it is affected by the brightness, but it doesn't seem to be affected in the correct way. Oh, and you know why? Because actually the epsilon coordinates for the texture are actually different from the epsilon position, actually the reverse of the epsilon position. So to get the correct epsilon coordinates for the texture, we should actually reverse them. So this is equal to 1.0 minus GLCORE dot epsilon. Now this should be correct. And let's try. Now, as you can see, the particles, when they are respawning, or actually even when they are spawned for the first time, they are always in the x that goes between -1 and 1, while actually we will be them overlapping. We want to have them overlapping with the image. So they should be spawned on a range that goes between minus image ratio to plus image ratio. So let's do that. Let's send this value here to our Jitter here. I just called it image ratio. Then I'm going to prepend image ratio. Actually, I'm going to use the camel notation here because I'm going to use it inside Jitter. So here I'm going to create a param, call it image ratio, give it a default value of 1. And then what we want to do is to basically multiply these values by image ratio. Right, the x position of the particles. So let's try, and now they are spawned according to the correct proportions. Very cool. Now the problem is that they are sampling the image according to this conversion that we did here. So the texture coordinates are still simply adding 1 to both the x and the epsilon position, which before, when the x was going between -1 and 1, this was working, but now it's definitely not gonna work. So we need to get also the image ratio inside the shader, because then we want just to sum it here to the image ratio and not to 1 for the x only. Okay, so I believe that there is a function that we can use which is called texture size. So let's create a new vector 2. Let's call it image size. From the image size, then we are going to be able to find the ratio of the image as we did it in Max. So this is called texture size, and it wants the name of our texture, which is called target image, right? Called it target image here, the sampler 2D. And then 0 is another argument, which doesn't interest us. We just set it to 0. Cool. So now let's create a float and let's call it image size ratio. And this is basically going to be image size.x divided by image size.y. And then what we want to do here is to, before we use the position.x to get the text score, we should divide it by the image size ratio. So let's do like this. Let's divide first that for a vector 2 that contains here image size ratio, and then 1 for the y, right? And then we sum that to that, and we multiply it by 0.5. Okay, let's see if this works now. I believe this is working. Yeah, it looks like it's working. Anyway, to be completely sure that this is working, let's go to the next step of our algorithm, which is basically setting the color, not to the input, but we can set it, so the color of the particles, we will set it to the pixel brightness. This is a vector 4 though, so we have to say vector 4 pixel brightness, since pixel brightness is just a float, so we need 4 of it. And cool, it looks like this is working. Let's do like this. Let's add the blending for the GGL mesh. So let's say here blend enable 1, depth enable 0. Let's see what we get. Right, let's disable this other video plane with the image. Cool, and now it's starting to look like the code from the tutorial. Awesome. There is one more thing we need to do, which is also done in the tutorial, in the original tutorial, which is every time the particles go below the bottom of the window, they need to respawn on the top, but at a different position. So this requires for us to create a random number inside our GLSL code, and this is not super trivial. Luckily, we can just ask ChatGPT to create a function for us. So can you create a function in GLSL to get a random number? And let's see what it gets us. That seems to be good. I haven't checked it. I don't know if this is actually a random number between 0 and 1. It says it is, so let's check it out. Let's go in our code and let's just paste what I just created, what I just copied. So yeah, there are a bunch of random numbers, and this just multiplies those numbers by a seed and then sum them and then makes the modulo of that and then divides it by this number, right? Seems to be, that should work. So let's go inside here. If new position is less than 1, our new position.x should be equal to our random. As seed, we cannot just use our actually input position.x multiplied by something random, right? So this every time should give us a different number, because every time the input position is going to be the result of the previous random operation. So this should actually work. The only problem is this is between 0 and 1, so we need to rescale that between minus the ratio of the image and minus the ratio of the image. So to do that, this is between 0 and 1, so we just subtract, now we just multiply first by 2. So because now it goes between 0 and 2, and then we subtract 1 to that, so it now goes between minus 1 and 1. And then we multiply it by the image ratio, right? This is how I call the image size ratio. Right, and cool, this should actually work. So let's go here. So now every time the particles go below the bottom of the window, they should then reappear on a different position here at the top. And I'm pretty sure this is working. Let's try maybe with another image. I have here this cyberpunk image. Yeah, that's pretty nice. It's a bit dark. So what I would like to do is to actually multiply this pixel brightness by 1.2. I'm actually setting it for all the values of the color. Actually, I should just set it for the alpha. So let's just try to set the red, green, and blue to 1 and the alpha to that value. Let's maybe let them go a bit faster when the image is dark, right? Anyway, we could also add more particles. So we could change this number to 20,000 here. So we will have double the amount of particles. Yeah, it's a bit too fast. So let's go back to like 0.004. Yeah, that's pretty cool. So what I did in my demo that I showed you at the beginning is that I made this video plane disappear after basically a frame. So it will look like the particles are replacing the image. So we can do that. I can send here this bang. And then I can say receive bang. Let's trigger 2 bangs from that. And the first is going to trigger a 1 for the enable. The second we are going to delay it like, I don't know, 60 milliseconds, and then we're going to trigger a 0. Also again for the enable. So let's see how this looks. Right. 60 milliseconds is a bit too few. Let's say 120. Right, and with the fact that this image is rendered to the main context, actually it will not be, will not have the tail that we can get from the slab here. So let's actually try to render it to the node. So let's render it to rain node, and let's see. And let's attach it actually to the texture, not to the matrix. Cool, so let's try if this works. Yeah, kind of gives this effect. Okay, let's try to reduce a bit the random speed, 0.01. Yeah, this looks better. Cool. Let's try again with the Fox image. We could add a bit of tail, so we can make this number smaller. 0.17 or something. What we could do also is to add a little offset to our brightness here. So add 0.1 as a brightness, as a little offset to the alpha of the color. So yeah, this now is a bit brighter, definitely. We can also maybe multiply that only by 1.1. Maybe make them go a bit faster here. Right. And I think this is basically it. So there we have it. Now, in the patch I showed you in the beginning, I add also another shader to render the particles of different sizes for the mesh. It's not necessary for the effect, it's just something that is nice to have. If you want to check out how I did that, you can download both this patch and the patch I showed you in the beginning from my Patreon for a little contribution. In this way you will support the channel and get access to the 100 of patches that I've been accumulating during the years of my Max career. One funny thing before we leave it is that we can actually, instead of using the color, only the brightness, we can actually use as a color the actual color of the image. So we can use like pixelval.rgb and then our pixel brightness here. So this will give us the color of the image, right? Start with the Foxy. Although I think for this effect, for how it is made at the moment, it works best with the black and white. So I just comment this out and just use the black and white version. So this was it. I hope it was not too confusing. If you have questions, you can always ask me here, or you can join my Patreon and have access to the Discord where I interact with my patrons. There's a big community there. So anyway, thanks so much for going with me through this madness. I really hope it didn't scare you, and I hope to see you in the next video. Have fun, people. Ciao.